If an electric field goes through a surface, how much of it counts? And how can we use this to figure out the charge inside of something without ever looking inside of it? This is exactly what Gauss's law answers. And the core idea is that Gauss's law connects the total electric field, so total electric field passing through a surface, to the amount of charge inside of the surface. It connects the two. And the field that's passing through, this is called electric flux. Electric flux is measured by this symbol. And in this video, I'll just be drawing it like this. Electric flux is a measure of how much electric field flows through a surface. Think how much field pierces through an area. Basic formula, keep in mind, this is not the actual Gauss's law. It's just a basic formula for a flat surface with electric field E and an area of A. The electric flux can be found, the E, the field, multiplied by the area, multiplied by cosine of the angle. This is the angle between the field direction and the normal. So if you don't know what the normal is, let's say you have a wall like that and your fields are going through this. The normal is perpendicular. So your angle is the angle between them. Here's some visual intuition for you. So I've gone and drawn a flat surface with an area of A and a uniform electric field passing through from left to right. But the surface is tilted. It's not flat to the field. The key here is the angle that's measured between the field and the perpendicular to the surface, aka the normal. That's important. Not between the field and the surface itself. So the perpendicular, or the normal, is in a direction like this. So the angle you use in your equation would be here, this angle right here, perpendicular to the area. And it works on the other side as well. Now if this was tilted, if you quickly try to imagine this with your head, it's tilted like this until this normal becomes parallel. That means the angle gets squeezed to 0. It becomes 0 degrees. Then your surface is fully open to the field. Goes straight through. There's no angle cosine in consideration. But what if the surface was rotated all the way around until it was parallel to the waves coming through? The surface is parallel. So that means the angle between the normal and the flux is now 90 degrees. Which means that the field simply glances past it. There's no flux. What counts as effective field? We don't care how long the field vector is overall. We care about how much of this field is pushing through the surface. That's why we take the component of E, which is perpendicular to the surface. Because if it comes in through an angle like this, then the flux would be the component of E that's perpendicular to the surface. Vector math is very important here. And because it's the perpendicular component, that's why we use cosine. Here we redraw E as a triangle, like this. The part of E that's perpendicular to the surface, the one that's actually contributing to flux, is labeled E with this symbol. This symbol means perpendicular. This is the effective field that pierces the surface. The rest just slides across and doesn't count toward actual flux. So no matter how you think about it, the flux is always given with our basic formula here. E, A, cosine. Either you use the full area value and the perpendicular component of the electric field, or you use the full E. So the full E as in the actual net vector magnitude instead of just the component. But then you have to use the perpendicular component of the area. We're going to go through some problems later. But here's a fun analogy. Flux is like rain hitting a roof. If you tilt the roof too steep, there's less rain hitting per square meter of roof. Does that make sense? Same thing with electric field and angled surfaces. And now we can scale it up. So instead of one flat surface, let's take a closed surface like a box or a sphere. I'll just draw a little box like this, and it wraps around some space. We can slice it into tiny bits, each with an area of A, as many as we want. And if we add up the field over all of these bits, then the electric field equation is the sum of all of the perpendicular electric field components passing through times all of the area, and it's the sum of all of them combined. This gives the total flux through the entire surface. Same thing, but we just consider all of it, everything, because it's a closed surface, it's not some flat thing like we were dealing with earlier. The actual Gauss's law is this: the sum of E perpendicular area equals the charge inside divided by this symbol, which is the permittivity of free space. This and every other formula is, of course, on the free cheat sheet in the description, and so is this number, which is roughly 8.85 times 10 to the power negative 12. This is actual Gauss's law. It connects the flux passing through, it connects it to the amount of charge inside our object. This is what we were building up to. The power of this law is that you don't need to know the charge inside. You don't even care what shape it is. You only care if you can wrap it with a surface and the field is symmetric, then you can calculate everything. It's like finding how many people are inside a house by counting the footsteps on the floorboards at the edge. It's cool. Let's go through an example. You have a tiny spherical shell, so the inside is empty, hollow, with a radius of 0.18 meters. And it carries a total uniform charge of positive 7.2 times 10 to the power of negative 6 coulombs. Find the electric field at 1 at a point 0.4 meters from the center, so outside the edge, and at a point 0.1 meters from the center, so that would be inside the shell. Here's a solution. We're going to go through it step by step. And if you haven't already, get the cheat sheet in the description for free. It's going to help us solve. It's going to help us solve this. Outside of the shell, our radius is bigger than the radius of our circle, which we'll just label radius of circle. Outside of a spherical shell, the electric field behaves as if all charges were concentrated at the center. So we can just use Coulomb's law for a point charge, which is also on the cheat sheet. And the formula is this. If we plug in all our numbers, so the charge, these numbers, everything, which I'm not going to write out because there's a lot of stuff going on. You get 405,000 newtons per coulomb for the electric field value. The field points radially outward, which means from the center outward, because the charge is positive. How about when the field is inside of the shell? It's zero. Trick question. It's zero. There's no solving. Because inside of a hollow conducting shell, there's no enclosed charge, which we talked about in the previous video. No matter how close you get to the inner wall, it's still zero. Time for a second example, because that one was really short. A large, flat conducting surface carries a uniform surface charge density of this. So it's this symbol equals 3.6 times 10 to the power of negative 6 coulombs per meter squared of area. Find the magnitude of the electric field just outside the surface. So we're told that this is the surface charge density. And there's a special formula we can get for this. Gauss's law gives us E times A for flux. And it's equal to the charge inside divided by permittivity. And this is equal to this thing, surface charge density times area over permittivity. So in this specific circumstance, the field just outside of a conductor's surface is given with this formula. And if you cancel out A, then the electric field is the surface charge density divided by this. So in this specific circumstance, we're allowed to use this formula. It only works because we're assuming a flat patch and E is perpendicular to the surface. It's not at an angle. If we plug in our value, so 3.6 times 10 to the power of negative 6 divided by the permittivity, which is, if you look at the cheat sheet, 8.85 times 10 to the power of negative 12. This is like a constant, so you don't have to memorize that. It's roughly 4.07 times 10 to the power of negative 5 newtons per coulombs of electric field power. This concept has been pretty abstract, and honestly, it's a little advanced. And I've tried to keep it a little simple, but this problem solving is difficult. So I'll just go through one more. Let's say you have two large parallel plates, and they're spaced 0.03 meters apart. The positive plate, let's just say the top one, carries a charge of 1.2 times 10 to the power of negative 5 coulombs. The plates both have an area of 0.15 meters squared, and what is the electric field between them? The plate separation is actually irrelevant here. We don't use Coulomb's law. This is a uniform field setup. And in a uniform field, Gauss tells us the electric field is equal to this symbol again, divided by the permittivity. And this symbol is represented by the charge divided by the area. Cheat sheet. The math. Well, first we have to solve for this guy so we can plug it into here. find the electric field. The charge is 1.2 times 10 to the power of negative 5, and the area is 0.15, giving us 8 times 10 to the power of negative 5. And we can plug this number here. So 8 times 10 negative 5 divided by the permittivity, which is 8.85 times 10 to the power of negative 12, giving us roughly 9.04 times 10 to the power of 6 newtons per coulombs for the electric field. The direction is straight from the positive plate down to the negative plate. It's uniform and straight.